Good afternoon, class.
Good
Good
afternoon, ma'am.
afternoon, ma'am.
So my screen is visible to all of
Good
you?
afternoon, ma'am.
Yes,
Yes,
ma'am.
it is visible.
Fine. So we had started graph theory in our previous lecture. Now today we are going to cover connectedness, Eulerian and Hamiltonian graphs, traveling salesman problem, and graph coloring. Fine. Now I am switching the screen. Are you able to view this screen?
Yes, miss.
Fine.
Yes, ma'am.
Fine. Connected graph. Here I am having a diagram of a graph. Are you able to view this graph?
Yes.
Yes, ma'am.
Fine. What is a
Connected
connected
graph.
graph? Yes, what is a connected graph? Yes, suppose this is a
All nodes
connected.
are connected to
Yes,
each other.
we can move from any vertex to any other vertex. Like this is the graph in figure 1, and we start from A, we can move to B, C, D, E, and back. From B we can move A, from B we can move E, from B we can come to D, from B we can move to C. It means from any vertex we can reach any other vertex. Fine. So their path exists between any two vertices. Fine. But this figure 2 graph, look at the figure 2 graph. Is this connected graph? Figure 2
No.
graph. No, it is not connected. Because from B we can't move to A. From C we can't move to A. From E we can't move to A. So figure 2 graph is not connected graph. It is not a connected graph. Fine. While figure 1 graph shown in the left hand side is your connected graph. Fine. Class, is it clear?
Yes.
Now see
Yes,
here,
ma'am.
figure 3. Figure 3. This is your figure 3. Fine. Tell me whether this is a connected graph or not. Figure 3 graph.
Yes, it is.
It is connected graph.
Yes,
Why
ma'am.
it is
It
a
is
connected graph?
connected.
See, from
We can reach
There is
both
path with
any
points.
vertex. Let us take vertex V1. From V1 we can move to V2. Yes. From V1 can be moved to V4. Yes. From V1 can be moved to V3. Yes. Fine. Is it clear? It means from any vertex we have a path to any other vertex of the graph. So this is an example of connected graph. Fine. Fine. Now you have different terms like paths, circuits, and cycles. My screen is visible to all of you?
Yes,
Yes,
ma'am.
ma'am.
yes, ma'am.
Okay. Okay. Now we
Yes,
have
ma'am.
three terms. One is path, circuit, and cycles. Fine. Yes. See, see this diagram. Figures X. See figure X. Okay. What we have to do, this X1, which I am highlighting red. X1 is our source vertex. Fine. And X12, right hand side, X12. This is our destination vertex. Okay. So we have to move from source vertex X1 to destination vertex X12. X12 is right hand side and X1 is at left hand side. So what will be the path? We can move here. This can be one of the path that I have highlighted with the yellow color. So this can be one of the path that I have highlighted with the yellow color. So what is this path? And how you are going to show it? You have started with the X. So we have written X, X1. Fine. Then X1 to X2, X1 to X2. Fine. Then you reached X2. Now X2 to X3, X2 to X3. Fine. Then X3 is there. Then X3 to X4. So now you are at X4. From X4 to X5, X4 to X5. Now you are at X5. From X5 to X6. Now you are at x6 and so on. Is it clear? I think path is clear.
Yes.
Yes, ma'am.
Fine, path is clear. Okay, this yellow color is one of the path from x1 vertex to x12 vertex. Fine, this is path. Is it clear? This is path, but this may be the shortest path, this may be the longest path. This is one of the path. Another path could be, another path could be that I am highlighting yellow color. It can be path, it can be one of the path, it can be another path that I am making here. This can be another path, but all the paths are of different length. All the paths are of different length, and we can't say that the path selected by us is the smallest path or the longest path. Fine. How can we know about it? If we are having weights associated with the edges, these are the weights. The weights can be in form of distance, like 20, 10, 5. suppose suppose this is a graph. Fine. A, B, C, and these are weights 5, 10, 15. So from A to C, we have total covered distance of 5 plus 10 is equal to 15. Is it clear? So these are the weights. If weights are associated, then you can calculate which path is covering the shortest distance or the longest distance. Fine. Is it clear? These are weights. And in any graph, if we put weights on edges, suppose this is a edge A, B, and this is a weight, then this type of graph is known as weighted graph. Weighted graph. Any graph in which we assign weights to the edges, fine, that graph is known as weighted graph. Fine. In case of problems related to distances, we usually assign weights to the edges to know about which one is the smallest path or which one is the biggest path. Weight is clear, class?
Yes,
Fine.
ma'am.
Yes, ma'am.
Or you can move, you can follow this path. You can follow this path. And what will be the total distance? Sum of the weights. Sum of the weights associated with the edges. Sum of the weights associated with the edges. Sum. Like 15 plus 10 plus 15 plus 30 plus 50 plus 30 plus 5 plus 5. This will be the. Now, if you select any other path, then what are the weights? You need to add those weights. Fine. So this is a path. Fine. Is it clear? Now coming on to walk. Now coming on to walk. Okay. Walk joins any two vertices. Suppose we have vertex V0 and we have vertex VK. So walk is joining the vertex. Fine. This is known as the initial vertex from where we start. Fine. And wherever walk completes, suppose we have traversed many vertexes and at last we have reached to VK. So VK is the end vertex of walk. And we can also name a walk. Suppose we say W. W is our walk. Fine. What is the length of walk? Suppose you have covered this. Fine. And how many edges are there in this walk? 3. Okay. This is U, this is V. How many edges are there? 3. So what is the length of walk? Length of walk here will be 3. 3 means number of edges that we have covered. Fine. In a walk, remember this. Remember this. In a walk, vertices and edges may be repeated. Vertices and edges may be repeated. For example, this is our graph. It is having vertex A, B, C, D, E. Fine. So what we are saying that vertices or the edges may be repeated. So you can start from here. See here, this vertex is repeated, A is repeated. Fine. You can again come back here. It means this edge is repeated. So in a walk, we have repeated this vertex, we have repeated this edge. So in a walk, vertices and edges may be repeated. Fine. You can repeat. See example. This is a graph. This is a graph. It is having how many vertices? How many vertices? 1, x1, x2, second, third is x3, 4 is x4, and 5 is x5. So you are having 5 vertices. 1, 2, 3, 4. 1, 1, 2, 3, 4, and 5. You are having 5 vertices. Fine. And what you have to do? You have to move from x1 to x5. Fine. You start 3, 4. So how many edges you have covered? You have covered 1, 2, 3, 4. Fine. You have covered 4 edges. So what is the length of this walk? Length of walk is 4. Length of walk is 4. Is it clear? Is it clear? And
Yes.
suppose you do like this. 1, 2, 3, 4, 5, 6. In this case, length of walk would be 6. Is it clear? Depending upon how many edges you have covered. Fine. Length of walk. Up suppose here we are having any one example. We have started from x1. See here we started from x1 this way. 1, 2, then we covered this 3, then we covered 4, then again 5, then again 6, 7. So we have repeated here, we have repeated here. This is a walk. Fine. 7. Is it clear? And suppose we have taken this direction 8. So what is the length of walk? Length of walk will be length of walk will be 8. Is it clear? Depending upon the edges that we have covered. And how you can write? You can write, you have started from x1, so simply write x1. From x1 you have moved to x2, so x1 x2. Now you are at point or vertex x2. Fine. So from x2 you have moved to x3, so x2 x3. Now you are at vertex x3. Fine. Now from x3 to x4, so you have written x3 x4 and so on and so on. Is it clear? So this is your walk of different lengths. Okay. Fine. Fine. A walk is called a path when, under which condition? Under which condition? A walk W is called a path if all its vertices are distinct and edges are distinct. It means walk will be known as path if all vertices are distinct, are unique, and all edges covered are unique. Fine. If there is no repetition in a walk, we can say that that is a path. But if there is repetition, it means this edge is repeated. It means this is not a path. It is simply a walk. Is it clear? Is it clear?
Yes, ma'am.
One thing,
Yes,
make
ma'am.
it very clear. When you come back to your own point, suppose you started at point 1, you move to point 2, you move to point 3, you move to point 4, again you come back to point 1. It is a closed walk. It is a closed walk. Fine. And open, suppose you started from 1, you move to 2, you move to 3, you move to 4, and you have not come back to 1 again. This is what? This is open. This is open. This is u, this is v. It means u is not equal to v. It means it is open. And this one where a cycle is being formed, From where you have started, you come back to that point only. That is a closed walk. Fine. Is it clear? So what is difference between a walk and a path? Yes.
Repetition of vertex and edges.
Yes. Path में, in path you need unique vertices. Unique. Fine. Unique vertex and unique edges. Edge or vertex should not be repeated. Fine. And what is cycle? What is cycle?
Cycle will be repeated.
Yes. Suppose this is A, we are forming a graph C, D. Without repetition, suppose you have started from the D, you come to A, B, C, and again to D. Then this is what? This is cycle. This is a walk which is in form of a cycle. It means the first vertex and the last vertex is same. First vertex and last vertex is same. So this is what? This is our cycle. Fine. Is it clear? What are components of a graph? Who will tell what are components of a graph?
Vertices and edges.
Yes.
Vertex edges.
Yes. Suppose this is a graph. This is a graph. So here all the components are connected. All the components are connected. And suppose this is a graph. So it has two components. It has two components which are disconnected. Which are disconnected. Is it clear? And here all the components are connected. Fine. Yes. Can you see these graphs on your screen?
Yes, ma'am.
Graph A. Graph A. Tell me whether it is connected or not. It is having connected components or not.
It is
No, it is
connected.
disconnected.
Yes, it is connected.
It is connected. See, from B I can move to A, to C, to D. It is connected. Fine. Now come to graph B. Graph B is also connected. From B you can come to D. From
It is
B you
also
can come to
connected.
C. From A to B, A to D is possible. A to C, A to D is possible. Fine. Coming back to third graph. That is graph C. See whether it is having connected components or not.
Yeah, it's not connected.
No. Fine. A and B, different sets. So this is what it is containing: disconnected components. Disconnected components. Can we move from A to B? No.
No.
Can we move from A to D? No. Can we move from B to C? No. D to C? No. Disconnected components. And there are two disconnected components. One is AC and second one is BD. Fine. Find all the components of graph G. Can you find all the components? Can you identify what are different components in this graph G? Class. See carefully. Yes. Can you see what I have highlighted?
There are,
Fine.
Yes,
there
ma'am.
are
One of the
basically
component. Fine. This one is another component. And this side, this is another component. See. This was the graph. And here we are having disconnected components. Yes or no?
Yes.
This one. This one is the this one is at leftmost side. This. Fine. Second one. See the second one. Second one is this. This is the second one. Okay. And here we are having third one. Third one is this. Is it clear? So it is having three disconnected components. That is first, second, and third. Three disconnected components. Fine. What is component of a G? It is maximal connected subgraph of G. Maximal connected. Fine. See. This is a graph. Fine. This is a graph G. Fine. And in this graph G, you have to find all the connected subgraphs of G. So what will be the connected subgraphs of G? Can you find connected
AB,
subgraphs of G?
AC, AD.
Yes. It can be AB. Fine. It can be AC. It can be BAC. It can be CD. Fine. It can be ACD. Is it clear? Class, is it clear?
Yes.
Yes.
So in
Yes,
this
ma'am.
way, you can write all the connected components. Okay. And what are disconnected component, disjoint components? 1 and 2. Fine. This is the first and this is the second disconnected components. They are disjoint components. Is it clear? Is it clear?
Yes.
Yes, ma'am.
Yes, ma'am.
Okay. Fine. Give an example of graph with components, each of which is complete. Do you know what complete graph?
Yes.
Yes, sir.
Complete graph. Suppose this is a point. This graph is having a single vertex. Now coming on to graph with two vertex. Is this a complete graph?
No.
No.
Why? Why?
All vertices are not connected.
Yes, complete graph. This is a complete graph because we are having only two vertices. Fine. Okay. From A to B we can go. Yes. From B to A we are having path. Yes. So it is a complete graph. Now coming on to A, B, C. See whether it is a complete graph or not.
Yes, it is.
It is
Yes,
complete
ma'am.
graph. From A you can move to C. From A you can move to B. Fine. From B you can move to C. From B you can move to A. From C you can move to A. From C you can move to B. It is a complete graph. Is it clear? So this one is complete graph. Graph number A, complete graph. What about graph number B?
Complete.
It's also
Yes.
complete.
Also complete.
Complete graph.
V1, V2, V3, V4. From V1, V2 is possible. You can move to V3. V3 is also adjacent. V4 is also adjacent. Similarly, take V2. Take for V3, V2, V1, V4. Fine. So all the components are connected. Is it clear? It is also complete graph. Now coming on to C1. C. Yes. V1, V2, V3, V4. From V5, you can move to V1. You can move to V2 directly. They're adjacent. V3 is adjacent. V4 is adjacent. And similarly for V1, similarly for V2, V1, V5, V4, V3. Coming on to V3, V2, V1, V5, V4. Is it clear? So this is also example of complete graph. Is it clear? Class, is it
Yes, ma'am.
clear?
Yes.
Yes, ma'am.
Now look at connectivity. This example I have taken from your book. I have copied this example from your book. Connectivity. How can we say that connectivity is disrupted? How can you remove the connectivity? See example of this graph. In this graph, you are able to view an edge. And what is the name of this edge? What is the name of this edge? D E.
D.
D E. Fine. If you remove this
DE.
edge, if you remove this edge, then the resulting graph is this. And this is what, suppose the name of this edge is E. So what this graph will be known as, resulting graph will be known as G minus E. E means removal of edge. Edge DE. So SDE general we are saying it as E. And how the graph will look? Graph will look like two disconnected connected components. Is it clear? Two disconnected components. Is it clear? So what we have seen?
Yes.
We have seen that removal of one edge can disconnect the. Is it clear, class?
Yes,
Left
ma'am.
hand
Yes,
side
ma'am.
graph is connected.
Yes.
Right hand side graph is disconnected because we have removed.
Ma'am, I don't know. I'm not hearing you. And also the presentation is stopped.
Me too.
Same here.
Me also too.
I think she is disconnected.
استاد خو لاړ ده. که چا سره اپډیټ هغه وي زموږ سکیجول نو هغه خو بیا ګروپ کې واچوي.
اپډیټ شوی نه ده، ما پخوانی یو سکیجول جوړ کړی و، بس نوی خو نه ده راغلی.
هغه کې چې وګوري تغیرات راځي که یو کلاس بل کلاس وګوري بل کلاس جوین شوی وي.
ورونو څه اپډیټ د اساینمنت باره کې خو څه نشته دی.
اسایمنټ پوښتنه باید وکړو، دا وخت ډېر کمېږي، هلته به امتحانونه روان وي، بیا اسایمنټونه وي.
سلام به همه شنوین دوستا. امی موضوع چی را استاد MCS212 را امو لب چی رقم کردین؟ امو به هیچ فهمیده نمیشه. من هر چقدر مسیج ماندم در گروپ کس جواب نداد. امو را یگان چاره نکنیم و شما یگان پیشنهاد تبدیلیش نکنیم.
به نظر شخصی من هر جایی که یا هر استادی که مقرر کرده باشین به نظرم تبدیل نمیشه، به خاطر که از اول تا بعد ما شما که چقدر درخواست کردیم یکشم یاد نظر نگرفتیم.
شاید اینمی تو باشه، راست میگم. سازا شاید تغییر نشه.
حالا دستن فهمت و بیستن پوت سیشن تیش در جایی فهمیدم نمیشه چی میگم. سخت هم هست.
تحمل
واقعا
میکنیم،
نمی‌تونم.
تحمل وقت دیگه چیز یاد گرفته نمیشه.
از ما
باز
استاد
تحمل میکنم.
چیز پیش استاد که می رفتیم، استاد سیسینه ما ضعیف بود برش می گفتیم، پیش عامر دپارتمنت می رفتیم که میره خبر ما تبدیل کنم، می گفت سیسینه چیز خود نکس فینیش نکس فینیش شما ایره یاد کرده نمیتونی. دو قسم سر ما استاد مقرر میکنیم.
بازی های امتحان های هم سخت سوالا میارن که تو سخت امتحان میگیری یگان تفگه دیگه معلوم
کوشش
شد.
کنیم که سمستر دیگه نبیایم.
ساز الکسیو تختیدله.
والا که ریکارد
امور
هم
از
بیاد.
ایالی اگر پیشنهاد کنیم که حداقل در دیگه سمستر نمانورم. ما گفتم در گروه عمومی یک پیشنهاد نکنیم ما شما که همین استاد ما درسایش نمیفهمید.
باشه که یک سمستر تیر شد که هیچی تو میشه.
والا
اینا یک
بیام
بار دیگه
خوارج
کنید.
سریم بعد
امیرا
امتحان بیا.
امو جک دنبا را بگوین بگوی اگر امکان داره می استاد بر ما میتونیش نمیفهم یک استاد دیگر را برای ما بیاره.
یا
چی میگه
کار
او باز
میکنیم
توضیح میکنه.
دمو گروپ عمومی که ما
برادر
پیام میمانیم
ریکارد
ما
چالا
دیگه
نشده.
او را چی کنیم او را کانفرم کنیم دیگه او تو میشه یا یک نفر از طرف کلگی یک
سلام
مسیج
ګروپ ملګرو ته زه په پښتو یو څه خبرې کوم د استاد په مورد.
صحیح
فکر
صحیح
کوم فکر کوم بدل به نه کړي ځکه هندوستان کې ما خپل بیچلر کړی دی، هلته به همدا رقم ته پیسټ کپي به وه د الګوریتمو په مورد. که څوک مثال غواړي چې ځان پکې ورسوي نو یوټیوب ته راجع کېدلی شي، او که بل استاد هم مقرر کړي همدې قسم ته به پیسټ کپي به وي، او فکر نه کوم چې دوی دا رقم استاد چې آپشن په آپشن تاسو ته تشریح کړي دغه پیسټ کپي به هلته هم وي.
او مشره دا سمستر کله اند کیږي؟ مال دا سمستر کله اند کیږي او اساینمنټونو حساب څنګه دی؟
بس چې هغه خلاص شي د کوم درسونه فکر کوم چې
لاس
څخه
په دې
ورسته
بیرته جوین شه هلته.
لاست 15 ورځې بعد کېدای شي د څو چې ختم دغه اساینمنټونه کېدای شي اپلوډ کړي ما په نظر.
ښه ډیر.
او نو استاد فکر کوم څه انتن باور نه کې ځکه چې دا خالي دومره ځکه امتحان دی پر نه راغو واسه تاسو کار نشئ ته اخیسته تاسو به چې مثال جی سی برغلی وي او موږ بیا اپلای کوو. ها
او بالکل ښه خبره.
او خالي دومره امتحان دی پر چې زده شي او نه فکر نه کوم چې موږ ته پر ځد واخلي آینده کې.
هغومره ان شاء الله خو د ټولو زده دي چې ماستري کوي انجینر صاحب دغه ټول ماشاءالله انجینران
ورونو
تکرار
وبخښئ استاده جوین
ټول
شوې ده لکه
ښکاري.
چې زموږ خبرو ته متوجه ده.
استاد جان
وایي
شوی
دا څه ګډوډ سره وایي.
Ma'am, you are joining but not appearing any presentation or something from your side. بیرته لاړه ده نو.
فکر کوم انټرنیټ کوم ستونزه لري.
مشکلات ده شي عزیز.
بالکل همداسې ده. ما خپل هم وروره 200 MB فایل کړ.
200 MB ډیر کار کوي.
والا څنګه وګورو.
ستا دغه یو ریکوست دغه تکو ده ICCR تکو چې تا د پر ځانګړی دغه وکي.
څه ورته والا چې وای اسمان ته مخې چې غږ دې نه راځي. بیچلر والا بیچارهګان ډېر چیغې ووهه خو سور یې ونه نیو.
Ma'am, are you there? If you're there and talking, we cannot hear you.
We cannot hear you, sir.
She is not, sir.
Ma'am, excuse me, ma'am, if you are hearing us, you are not audible now.
We can't hear you, ma'am.
My screen is visible to all of you.
Yes,
Yes,
My
ma'am.
screen,
yes, ma'am.
Just now it's
fine,
visible.
fine.
Yes.
So
You
now,
are
Just
now
now.
you have learned about
audible.
connectivity. So what we have done, we have removed one edge from graph G, and now the graph has become disconnected because it is having disconnected components. Fine, fine. So what we have done, we have removed this edge. We have removed this edge to form two disconnected components. Fine, fine. Is it clear?
Yes, ma'am.
Okay. What
Yes,
about
ma'am.
this graph? Can you say anything about this graph? In this graph, there is no bridge. No edge is a bridge. So how can you form it into, how can you convert it into two disconnected components? Is it possible? Is it possible?
It is possible if we delete many edges.
Yes, more than one, more than one edge. More than one edge. Fine. Can you find the bridges in each of these graphs? What is a bridge? This edge. This edge BC is acting like a bridge. Just remove this edge. If we remove this edge, what we get? We get A, B, and C, D. Two disconnected components. Is it clear? See this diagram, B diagram. Is there any bridge in this diagram? B, B1. Yes.
Yes,
Can
ma'am.
you name?
U1 and U6.
U6, U3.
U1 and U6.
Okay, fine, fine, fine,
And also U3 and U6.
U6 is 5.
fine. Yes, you can
That is
remove
with
it.
me.
Remove it.
U3.
Then what will be having? This
U5 and
and
U6.
this. Fine. Is it clear? Good. Good. Okay. If you remove the edge DE, the resulting graph gets disconnected. Fine. Okay. Yes. And what do you mean by edge connectivity? Edge connectivity. What do you mean by edge connectivity? It means the number of edges that we want to remove to make graph disconnected. Fine. Fine. In this graph, tell me how can we make it disconnected? What we have to do? This is graph. Yes. How we can make it disconnected?
Can remove the HWY and also VX.
Yes. And we all can have different views. Fine. But one thing is clear, that we can remove the one edge or more than
The edge from
one edge.
voice is very
One edge or more
W.
than one edge to form the disconnected components. Fine.
WY.
Okay. Now see this diagram. This is a graph. Fine. This is a graph. How can you make disconnected components? Yes. What you can do?
If we
XV. You can
X and Y we
make
eliminate.
XV and VU. If you remove both the edges, then what you will get? UWY. Fine. UWY. Why? Will it make disconnected? Will it make graph disconnected or not? Tell me. Will it make graph disconnected or not?
Yeah, we can remove one edge, for example, XZ or YZ.
U is removed. U is removed. है ना? Fine. U is removed. So yes, U is removed, and here V is removed, and here X is removed. When X is removed, can you form a link from X to Y or not? Yes or no? For an edge, we need two vertices, V1, V2. Suppose we remove V1, then what it will form? It will form V2, because only V2, because we are not having V1 anymore. So this edge will not exist. Fine. Fine.
Yes, yes.
Yes. So here we can remove multiple edges. And what pairs we have formed? UW. UW is this one. UW. Then UX. UX is this one. And then third one is VX. We have removed this. It will break the graph into two disconnected components. Is it clear, class? Is it clear? Class?
Yes, yes.
Yes,
Yes, you
yes.
can have multiple combinations. You can have multiple combination. I will provide this presentation. You can try with different options. Fine. Like I have taken this SUSV. SUSV. Fine. Again, there are many possible combinations. You can try this out. Fine. Then what is cut vertex? So cut vertex of any connected graph is a vertex which, when removed, makes the graph disconnected. For example, in this graph, let me take D. Let us remove D. If I will remove D, the graph disconnected components will be like this. Fine. Is it clear? Is it clear?
Yes,
E,
yes, ma'am.
F, G, H. There will be two disconnected components. So in the similar way, we can remove E also. We can remove E also to form the disconnected components. So we can say D and E are cut vertices of the graph. Fine. Then what do you mean by graph isomorphism? What do you mean by graph isomorphism? Yes. A graph will be having same number of, we will have two graphs. They will be having same number of vertices. Same number of vertices. Same number of vertices. Same number of edges. Same number of edges. But only representation will vary. But only representation will vary. This is known as graph isomorphism. Suppose we have one graph named as G1, another graph named as G2. Okay. For even edge, we have corresponding edge in our graph G2. For any set of vertices, we have corresponding set of vertices in the next graph. And the graph we can represent like V1 E1 and V2 E2. So in general, we can say that isomorphic graphs are those graphs that are having same number of vertices, that are having same number of edges, but they're they are having different representations. Different representations. They're having different representations. See the example of isomorphic graph. My screen is visible to all of you?
Yes, it's
Yes, ma'am.
visible.
Okay. See, count the number of vertices. A, B, C, D, E. Here we are having 5 vertices. P, Q, R, S, T. Here also we are having 5 vertices. Okay. Then number of edges: 1, 2, 3, 4, 5, 6. 6 edges. Let us count here in right hand side. 1, 2, 3, 4, 5, 6. 6 edges. So in both the graphs, we are having 6 edges and 5 vertices. Okay. Only the way of representation is different. See here. Only way of representation is different. Yes or no? Otherwise, both the graphs are same. So we can say these are what? These are your isomorphic graphs. Suppose you have to find whether two graphs are isomorphic or not. First count the number of edges in both. Then count number of vertices. Fine. And then see whether there is a correspondence, like point A is corresponding to point B. See the correspondence between the set of vertices in both the graphs. Okay, diagrammatically they need not to be same, because we are saying then isomorphic graphs, number of edges and number of vertices need to be same. Representations may vary. Is it clear? Representation may vary. See, can you tell whether A and B are isomorphic or not? Yes or no?
Yes, yes.
Yes,
Yes,
they are
yes.
isomorphic. They are isomorphic, but the way of representation vary. Fine. Count number of vertices: 1, 2, 3, 4, 5, 6, 7, 8. And in B, 1, 2, 3, 4, 5, 6, 7, 8. Is it clear? Is it clear?
Yes, ma'am.
Now
Yes.
edges: 1, 2, 3, 4, 5, 6, 7, 8. In this way, you have to count the edges. Here also, in this way, you have to count the edges. And see, the number of edges and number of vertices are same. Only the representation is differing. So these two are examples. A is isomorphic to graph B. Fine. Is it clear, class?
Yes, ma'am.
Now coming on to bipartite graph. Bipartite graph. Fine. Can you see this diagram?
Yes.
Can you see this diagram? See, we have one set of vertices, yeah, one group of vertices here: x1, x2, x3, x4. We have another group of vertices here: y1, y2, y3, y4. For example, x1, x2, x3, x4 represent the persons, and y1, y2, y3, y4, y5 represent the jobs. So this diagram shows how a particular person do a particular job. Fine. This x1 is doing job y1 and y2. Person x2 is doing job y1 and y3. X3 is a person who is doing job y4, and so on. So how this is represented? This is represented in form of a bipartite graph, in which we are having two sets here, two groups of vertices. One is x1, x2, x3, x4, and second one is y1, y2, y3, y4, y5. And how will you remember? How will you identify whether a graph is bipartite or not? How? Suppose these are our vertices y2, y3, y4. They belong to one set. Here we are having vertices x1, x2, x3. They belong to one set. See that there should not be any edge between the vertices of the same set. Is it clear? There should not be any edge between the vertices of the same set. This is not allowed. Only there should be edges between vertices of different sets. These are allowed. Fine. These are allowed. These are allowed. But x1 it can't connect to x2, or x2 can't connect to x3, or y1 can't connect to y2, or y2 can't connect to y3, or y3 can't connect to y4, and so on. Is it clear? Is it clear?
Yes, yes,
Yes.
ma'am.
So there will be two groups of vertices, and within a group there should not be any edges. There should not be edge. Fine. So see the edges. E1. E1 is from x1 to y1. E2. E2 is from x1 to y2. So see the edge E1. In E1, X1, Y1. X1 is from this group and Y1 is from this group. Is it clear? X2 to Y3. X2 to Y3. Suppose this is E3. So E3, X2 is from this group and Y3 is from this group. So this is an example of bipartite graph. Yes. Can you tell whether this example shown here is of bipartite graph? Yes or no? Yes, class? Is this an
Yes.
example of bipartite
No.
graph or not?
Yes.
Yes.
How you can say? How you can say?
Two different colors are connected.
Two different colors are there. A, B, C, D. So one set is A, B, C, D. They are represented with a black. Fine. And what is the another group? Another group is represented with the help of suppose E, F, G, H. E, F, G, H. They are represented with a red color. And see any edge. Just look at any edge. A, H. A, H. See the
Arif,
A,
please
H.
mute.
Yes. See the H, A, H.
Arif,
See the
mute
H,
yourself,
A, H.
Arif.
Switch your mic.
Yes.
Switch off.
AH. AH is connecting. AH is connecting A and H. So A belongs to this group and H belongs to this group. Is it clear, class? See the H,
Yes,
B,
ma'am.
C, B, F.
Yes,
B, F.
ma'am.
See B, F. B is connecting with F. They are from different groups. Then see the H, D. H, D. This is DH. D is from this group and H is from this group. So this is an example of bipartite graph. Is it clear?
Yes.
Is it clear?
Yes, ma'am. Yes.
Okay.
Yes, ma'am.
Now coming on to complete bipartite graph. Complete bipartite graph. What is mean by this complete bipartite graph? What does this mean? Yes.
Every vertex of one group is connected
Yes.
to other vertex of other group.
Yes. Vertex of one group is connected to every other vertex of another group. See, one is connected to one of second group. One group is shown with the help of black color and another group is shown with the help of blue color. So see, one is connected to one is connected to 5 of other group, one is connected to 4 of other group, one is connected to 3 of other group, and one is connected to 2 of other group. And how we can represent 1 for this and 5? 1, 2, 3, 4, 5. K1, 5. It is representing bipartite graph K1, 5. See, K1, 5 can also be written like this. This is one group and this is another group, and member of vertex of this group is connected to all other vertex of another group, shown as vertices of blue color. So this is again example of complete bipartite graph. Yes, class. In this diagram, suppose one group vertices are shown as green color, V1, V2, V3, and another group vertices are shown with the blue color. Okay. P1, P2, P3, P4. Now tell me whether this graph represent bipartite graph or not. Why or why not? Tell me. See the edges. Each edge is connecting members of different groups. See. Fine. Is it clear?
Yes.
See each edge is connecting member of different group. One from this group and another from this group, blue group. And there is no edge which is connecting members of same group. There is no edge which is connecting members of same group. Yes or no? So this is again an example of bipartite graph. And combination C, there are three vertices. V1, V2, V3. So K3. In this group, we are having 4 vertices. So 4. So this bipartite graph is represented as K3, 4. Is it clear? Class, is it clear?
Yes, yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So this is an example of K33. Suppose here we are having red group and there we are having blue group, and see every edge is connecting one member from left group and one member from right group or right set. Fine. And is there any fault? No. If there would have been fault, then it means this would have been connected. So it is not there, so it is okay. This type of edges should not be there that I have labeled with the green. Fine. So it is again example of complete bipartite graph. So yes, name the groups. Can you name the elements of group? What are the elements of first group?
V2, V4.
Yes.
V1, V3 and V2, V4.
V1 and V3. Okay. Another group is V2 and V4. And see this V2. See this V2. V2 is connected to another group, to V1. See here V2 is connected to the member of another group. Is it clear? Is it clear?
Yes, yes, ma'am. Yes.
Okay. Now trees. You have studied trees? You have studied trees?
Yes.
Yes.
Yes,
Yes.
ma'am.
So how can you represent trees? How can you represent trees like this? These are what? These are nodes.
Yes,
Correct.
ma'am.
Yes,
No.
these are nodes. Fine. And there is no cycle in a tree. There is no cycle in a tree. This is parent node. These are child node. These are child node, or we can say these are siblings. These are child nodes, or these are siblings. What is the characteristic of a tree? What is characteristic of a tree? A tree should not contain
Cycle.
a tree. Yes, a tree should not contain a cycle. This is a tree. It should not contain a cycle. If we join these two nodes, it means we have created a cycle. This is not a tree now. This has now become a graph. Fine. This we have studied earlier. See two diagrams. One diagram. In one diagram we are having graph G, and in another we are having graph H. Are you able to view the two diagrams?
Yes, ma'am.
Yes.
See, in G, fine, we are having no cycles. Is there any cycle? No. And why we are writing disconnected? Just tell me why we are writing disconnected here. Disconnected
X4
X4 has
is
no edge
because
whatsoever.
of X4. X4 is disconnected from other nodes. So is this a tree or not?
Yes, ma'am. It doesn't have a cycle.
No, this is not a tree. Not a tree. Because in a tree, every component should be connected. But as we can see that X4 is not connected. It is disconnected. So we can't say that this is a tree. Is it clear? Class,
Yes.
is it clear?
Yes, ma'am.
Yes, yes, ma'am.
If it would have been a tree, it should be like this. X4 should also be there. So this is not a tree. Coming on to right hand side. Come on to right hand side. Is there any cycle? In right hand side, is there any cycle?
No.
No cycle.
No,
Okay.
ma'am.
Are all components connected? Y4, Y3,
Yes.
Y2, Y1, all are connected? Yes. So
Yes,
all
ma'am.
are connected and there are no cycle. So this is a tree. Is it clear?
Yes, ma'am. Yes.
So what is the property of tree? All the components should be connected
Connected.
and there should be no cycle. Is it clear?
Yes, ma'am.
Is it clear?
Yes,
Yes, yes.
Yes, ma'am.
all the components should be connected. All the components should be connected. All, see here, all components are connected and there is no cycle. So we can say this is a tree. So property of tree, it means there should not be any disconnected component. It means all components should be connected and there should be no cycle. So we can define tree. A tree is a connected graph with no cycles. Clear?
Yes, ma'am.
Clear? Tree is a
Yes,
connected
yes.
graph with no cycles. Fine. And what is a forest? A forest is a graph, each of whose components is a tree. This is a tree? Yes. This is a tree? Yes. This is a tree? Yes. Fine. This is a tree? Yes. And what all this represent? It represents forest. So forest is a graph. Forest is a graph, each of whose components like A, B, C, D. These are components of forest and every one is connected. Everyone, this is a connected component, this is connected component, this is connected component, this is connected component. Fine. So this is tree, this is tree, this is tree, this is tree. So this complete represents your forest. Is it clear, class? Is
Yes,
it clear,
ma'am.
class? So forest is a graph, each of whose components is a tree. So this collective is your forest. Fine. So this is a graph. How many components it is having? Tell me. How many components are there in this graph?
4.
4. Fine. 4 disconnected component. This is 1, this is 2 component, this is 3 component, and this is 4 component. And each of these component is a tree. This is a tree. Tell me
Yes.
why this is a tree. All are connected.
All.
Yes.
Yes.
No cycle.
No
Yes, this
cycle.
is a tree. Yes. All are connected. Yes. There is no cycle. Very good. This is also a tree. This is a tree. Yes. All are connected. See, all are connected. See, all are connected. Fine. And there is no cycle. This is also a tree. Here, this is a tree because all are connected. All are connected. All components are connected and there is no cycle. So 1, 2, 3, 4 are the components of a graph and all these components are tree and this complete is your graph. Is it clear, class? And this graph is also known as forest because it is collection of trees. Clear?
Yes, ma'am.
Yes, ma'am.
Now coming on to spanning tree for a graph G. What do you mean by spanning tree? Spanning tree
Subgraph
will
of
be,
G.
yes, very good. It will be the subgraph of your graph. Fine. And what is its property? This graph, subgraph should have all the vertices of the graph. Should have all the vertices of the graph. Okay. First, it should have all the vertices of graph, and second, no cycle should be there. No cycle should be there. Okay. So how can you find the spanning tree for a graph? You have to form a subgraph. Conditions, what are condition? Number 1, all the vertices of the graph should be present there, and second, there should not be any cycle. See here. Are you able to view my screen? Are you able to view
Yes.
my
Yes.
screen?
Yes.
We have a graph. We have a graph G. You have to find the spanning trees. You have to find the spanning trees. See in diagram. Yes, T1. See in diagram T1. X, Y. Fine. Suppose this is Y dash, Z, W. How many vertices are there? 1, 2, 3, 4, 5. Now let us see at the graph G how many vertices are there. 1, 2, 3, 4, 5. It means number of vertices are same. Number of vertices are same. Is there any cycle? See T1, is there any cycle?
No.
No, no cycle. No cycle. It means T1. T1 is spanning tree of graph G.
No.
Is it clear, students? It means T1 is a spanning tree of graph G. Now check for T2. See the number of vertices. 1, 2, 3, 4, 5. Fine. And in G we were having 5 vertices. So number of vertices are retained. Now check for the cycle. Is there any cycle? In T2, is there any cycle?
No.
No. So it means T2 is also the spanning tree of graph G. Is it clear? Can you draw the spanning tree of this graph visible on your screen? Let us try. Fine. We should keep in mind two things. First, number of vertices should be same. Should be same as that of original graph. And second, what is the second point? There should be no cycle.
Cycle.
Fine. Okay. Is it clear? See, 1, 2, 3, 4. 4 vertices. So 1, 2, 3, 4 vertices. Or is there any cycle in graph that I have drawn? Is there any cycle?
No.
No.
No. So it means this is B is spanning tree of A. B is spanning tree of A. Is it clear? Is it clear?
Yes.
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 It should have
It
4
can
to
be
5
like this also.
vertices.
It can be like this also. E, A, D, C. See the number of vertices. 1, 2, 3, 4. 4 vertices. Okay. Is there any cycle? No. Is there any cycle? No. So we can also say that C is, yes, spanning tree of A. Clear?
It's not Spanish.
It's not spanning tree. Why?
4 vertices, there
नहीं,
is
ये
5.
ये ठीक है. This was missing. By default, this is here. Fine. This is the fifth one. Na? This is the fifth one. By default, it was missing. So it exists there. I have not shown it exclusively. Fine.
Yes.
See here in these diagrams, I have shown this vertex exclusively. This is here. Done. So for the above diagram, we have made 3 spanning trees. What can be other spanning trees? See, 1, 2, 3, 4, 5. There are 5 vertices. So 1, 2, 2, 3, 4, 5 vertices. 1, 2, 3, 4, 5 vertices. 1, 2, 3, 4, 5 vertices. Fine. Is there any cycle? No. Is there any cycle? No. Is there any cycle? No. It means all these 3 are the spanning trees of graph G. Is it clear? Can you draw any other spanning
Yes.
tree? Can you draw any other spanning
Yes.
tree? How?
A1 to EC.
Yes.
Counting the edges.
Yes.
By counting the edges, we can draw.
Yes. See my diagram, topmost right hand side. See, first vertex,
We can
second,
just
third, fourth,
remove
five,
the
and
A1.
5 vertices, and there is no cycle. So again, this is the spanning tree. Is it clear? Is this diagram is clear?
Yes.
Done.
Yes.
Okay. Done. Fine. Now coming on to Eulerian graph. This is another booklet. We had started from earlier, we had completed first book in our previous class where we started the graph theory. Fine. And we started today with the connectedness. Fine. And now we are here. Eulerian and Hamiltonian graphs and traveling salesman problem. These are different booklets. First was graph introduction. Second is about connectedness. Third, Eulerian and Hamiltonian. And fourth for the graph coloring. Fine. Complete graph block. Bipartite graph, trees, forest, spanning tree. Fine. Now coming on to Eulerian. My screen is visible to all of you?
Yes, it's visible.
Okay. E. Keep in mind E. E for Eulerian or E for H. This will help you in remembering the Eulerian graph. E for Eulerian and E for H. Fine. A connected graph is Eulerian. It means it will be having a closed trail. Closed trail that includes every edge. It means like this. It means if in your graph you are having edges like this, so Eulerian trail will cover all the edges. It will also cover edge E2, it will also cover edge E3, it will also cover edge E4. Such a trail will be known as Eulerian trail. And a graph having Eulerian trail will be known as Eulerian graph. See, this is diagram. You have to find whether the graph is Eulerian or not. You have to check for the edges. Every edge should be covered. Fine. Every edge should be covered. So how we find out whether a graph is Eulerian or not? We start reversing. Suppose we started from D. This edge is covered. Fine. Then again you move through diagram this. You move through B, from B to F, from F to A to B. You have to see that each edge is covered once. Fine. Now see, I have started with D. I reached D. C. From C, I reached B. From B, I reached A. From A to F. From F to E. And from E to D. Am I able to traverse all the edges through this? Yes or no? Because these edges are left. So it means I need to change my strategy. So what I did, let me create. This is the graph. Class, are you able to view my screen?
Yes.
Okay, this is a graph. Let me draw the graph. Fine. And what are the vertices? A, B, C, D, E, F. Fine. Now let me start reversing. Fine. Let me start from here. I started from here. Fine. What I done, I move here, then B to A, then A to F, then F to B. Fine. Then here in this manner, then from F to E, then E to G, then G to C, then C to E, and from E to D. So I have traversed all edges, all edges, all edges. This graph, it means this graph is having Eulerian trail, as we are able to cover up every edge of the graph once. So if this graph is having Eulerian trail, we can say this graph is Eulerian graph. Is it clear, class? All the edges once. Yes, class?
Yes, ma'am. Yes, ma'am.
Have you seen Eulerian trail? Yes, class. Have you seen Eulerian trail?
Yes, ma'am.
What I
Yes,
have
ma'am.
done, I have covered
All is
every edge, exactly once. Every edge is covered. See, every edge is covered. So this is what? This is Eulerian graph. This graph is Eulerian. Is it clear? Class, is it clear?
yes, ma'am.
In Eulerian graph, what you have to do? You have to, yes, you have to cover all the,
All the edges once at
yes,
least.
all the edges once. All the edges once. This is like a game that we used to play in our childhood days. That just hold on the pencil and just start covering each and every edge of the diagram given to us. This is Eulerian trail. Can you find whether the above graph is Eulerian or not? Just try. Just try. What I did, I started from here. Yes, this started from here, moved here, again to this vertex, coming back. See, is every vertex covered? Sorry, is every edge covered or not?
Yes, it's covered.
Suppose this is your diagram. Fine, you are having A, B, C, D. Fine. Now let us see. A to B. Okay, this edge is covered. Fine. Then this is also one of the edge, E. This is vertex E. It is forming edge BE. Then this, coming here. See, all the edges are covered. All the edges are covered. Fine. Exactly once. So we can say this graph is Eulerian graph. Done. Now you can identify whether a graph is Eulerian or not. Class. Yes or no? Class. Suppose you are having graph G. Are you able to view graph G?
Yes, ma'am.
V1, V2, V3, V4. Is this Eulerian or not? How can you find is this a Eulerian graph or not? See, let's start reversing. I have started from here. This. See, what all possible combinations could be there? Are you able to cover every edge? Just
No,
check
ma'am.
on your own. Are you able to cover every edge?
No, ma'am.
One edge is remaining. In
Yes.
my case, one edge is left. Which one? This one. I was unable to cover this edge. If you are unable to cover even one of the edge, then the graph is not a Eulerian. So this is not a Eulerian graph. See the right hand side graph. Here I was able to cover the edges shown with the green arrows, but I was unable to cover this edge. So this graph is not, again, Eulerian, not Eulerian. Fine. And how can you identify whether a graph is Eulerian or not? A connected graph G is Eulerian if and only if degree of each of its vertices is even. This is theorem. Fine. If degree of each of its vertices is even. Fine. In this way, you can find whether a graph is, yes, Eulerian or not. See, in this diagram, A, B, C, D. What is degree of vertex A?
2.
What is degree of vertex A?
2.
2.
2.
So it is even. What is degree of vertex B?
2.
2.
2. It is even. What is degree of vertex D? Even. 2. Degree of vertex C?
2.
Yes. Is it clear? Coming on to this diagram, degree of vertex 2, degree of vertex 4 even, degree of vertex C 4 even, degree of vertex B 4 even, degree of vertex F 4 even. Fine. So this will help you. Now coming on to Hamiltonian graph. Hamiltonian graph. Fine. Hamiltonian graph will be having Hamiltonian path. And what is Hamiltonian path? Hamiltonian path is a path which covers every vertex of the graph exactly once. Here we are concerned about the vertex, not the edge. It will cover, Hamiltonian path is going to cover every vertex of the graph exactly once. Fine. And this is known as Hamiltonian cycle. Fine. Hamiltonian cycle. See, this is a graph G. Now we are concerned about the vertex. Fine. Let's see. Let's start from here. We have to cover every vertex exactly once. So we started from here. We have covered D. Fine. We have covered C. Moving ahead, we have covered B. Moving ahead, we have covered A. We have covered F. We have covered A. We have covered E. Coming back to D. Right? Few edges are remaining. Few edges are remaining. So we need not to concerned about the edges. We are concerned about the vertex. So we have covered all the vertices. All the vertices exactly once. So this graph is our Hamiltonian graph. Is it clear, class?
Yes.
Yes.
What is difference between Hamiltonian and Eulerian?
I think,
On vertex.
Yes. Yes.
yes, ma'am. I think the Himalayan and Illyrian. Illyrian graphs can be Hamiltonian, but Hamiltonian cannot be Illyrian.
Good. So, in case of Eulerian, we have focused on covering each x exactly once. In case of Hamiltonian graph, we have to cover each vertex of graph exactly once. Fine. Check for Hamiltonian. Is this a Hamiltonian graph? Check.
No, ma'am.
Why?
Because the middle vertices will be covered twice.
There is a repetition. Na? See, there is a repetition. So you have to cover vertex only once. Each vertex only once. Suppose I start from here. Okay, this has been covered. Now this vertex is covered. Now this vertex is covered. This vertex is covered. This vertex is covered. Again coming here, but this was already covered. We have to cover each vertex only once. So this is not an Hamiltonian graph. Is it clear, class?
Yes.
So check for this. Check this graph for Hamiltonian. Check this graph whether it is Hamiltonian or not.
Yes, it is Hamiltonian.
Yes. Yes. Suppose we started from here. So this we have covered. C we have covered. B we have covered. F we have covered. And we are covering all only once. G we have covered. Fine. So all 5. We have covered all 5 vertices once only. And all have been covered. You need not to bother about these leftover edges. Fine. Check for Hamiltonian. Yes. Covered. This is covered.
Yes.
Moving ahead. Covered. Fine. Is it clear? So this is Hamiltonian graph. And what a non-Hamiltonian graph? Yes.
Trees.
Yes. Trees. Trees are any tree. It is non-Hamiltonian. There is no cycle because in tree there is no cycle. So it is non-Hamiltonian graph. Fine. Is it clear? See, this is a graph. Is this Hamiltonian or not? So just see carefully. Here in this graph, you can see a cut vertex. Cut vertex matlab, what do you mean by cut vertex?
Repetition.
Yes, if you will remove this vertex, this graph will become disconnected. Fine, because it is connecting both the triangles, upper triangle and lower triangle. Because of the presence of cut vertex, see, if I try to find Hamiltonian trail, fine. Suppose I proceed like this coming on here. Somewhere I have to cross it again, but it was already crossed. So it means because of this vertex, there is some problem. Fine. Because while traversing, I need to traverse this 2 times to come back here. So this should not be done. So we can't say that this is a Hamiltonian graph. This is non-Hamiltonian graph because of presence of this cut vertex. Is it clear? Is it clear, class? Is it clear? Please
Yes,
respond.
ma'am. Yes, ma'am.
Respond. Then coming on to traveling salesman problem. See here at the bottom right hand side, I am drawing a graph. I have graph G1 and I have one more graph G2. In graph G1, I have vertices A, B, C. In graph G2, I have vertices P, Q, R. Fine. And here I have associated weights 50, 20, 30. So this is simple graph G1. But G2 is a simple graph which is also known as weighted graph. Weighted graph because I have associated weight with every edge. Is it clear? So this is what? Weighted graph. Because every edge is showing some weight. And these weights may be cost or distance. For example, for some traveling problem, we can associate this as 50 is a distance covered. 50 is distance covered. 20 is distance covered. 30 is distance covered or distance between Q and R. So this is what? This is your weighted graph. Is it clear, class? Now you can identify weighted graph. Fine. So traveling salesman problem. In traveling salesman problem, there is a traveling salesperson and he has to visit every city exactly once. And these are cities T, L, M, N, O, P. And these are weights associated. Suppose this is an H from P, L, and this is the weight associated, that is 51. This is weight associated. This is suppose distance between P and L. Distance between P and N is 51. Distance between T and L. T, and L is 60. And this is an example of weighted graph. Is it clear? What are towns? L, M, N, O, P, T. These are different towns. And a salesperson, traveling salesperson, has to visit every town exactly once with minimum weight. Is it clear? Minimum weight, it means minimum distance, because while minimizing distance your cost will reduce. Is it clear?
Yes.
Now you know the question, you know the problem. There is a traveling salesperson and he has to visit every town. Town is L, M, N, O, P, T. And he don't knows which will be the best path. He don't knows which will be the best path through which he will cover all the cities, covering minimum distance. Thus, this is an example of optimization problem where the best route has to be found. Is it clear? And these are weights 56, 21, and these lines are representing roads. These are the roads which are connecting different cities. Is it clear? Suppose this T can be your Tamil Nadu. Fine. M can be your Mumbai. So what is distance between Tamil Nadu and Mumbai? This is represented by 70. Is it clear? This is 70. So how can we solve this problem? We have to construct a Hamiltonian cycle of minimum weight. For solving this problem, we have to construct a Hamiltonian cycle, because in Hamiltonian cycle we cover all the vertices, and here our cities are like vertices. So we have to cover all the vertices with minimum weight. We have to construct Hamiltonian cycle of minimum weight. Fine. Just start. Let us take one cycle. One possible cycle can be we start with L, move to M, M to N, N to O, O to P, P to T, and T to L. This can be one possible cycle. So what can be weight associated? It will be sum of all the weights. So from L to M, what is the weight? Class, from L to M, what is the weight?
56.
56. Fine. From M to N, what is the weight? 21. From N to O, what is the weight? 36. From O to P, what is the weight? 51. From P to T, what is weight? 13. From T to L, what is the weight? 60. Suppose this comes out to be some value. Now, we can find other routes through which the total weight could be minimized. So instead of coming here from L to M, you can find another route through which distance could be minimized. So our problem is like this. Instead of this LM, fine, you can find another route, or instead of this MN, you can find another route. So see, our initial routes were like this. We had started from here. So our original graph that we created was like this: L to M 56, M to N 21, N to O 36, O to P 51, P to T 13, and T to L 60. Fine. Later on, see, some new paths are formed, like MP, because its weight is less. So some, in every stage, some new paths are added and the old one are deleted, like this has been deleted, so this is not here. Fine, this PO has been deleted, so it is not here. In every step, to optimize, that is to find the minimum distance, these routes are being changed, and every step some new route is added which involves minimum distance to be covered. And finally, see, our graph turns out to be like this. And see, in this graph, your weight will be total 70 plus 35 plus 21 plus 2 plus 51 plus 31. And this is your minimum weight. And the first step, the path that we were covering, was having the maximum weight. With series of modification and selection of paths with the lower weights, now you have optimized solution. Fine. In this way, the traveling salesperson problem is solved. Try out with this example. And here I have mentioned how we have gone for this, how we have replaced, which paths were having more distance, which were covering lower distance. And what we found that the overall cost, yeah, overall distance of traversing all the vertex of the graph is now reduced, and the final graph is like this. Fine. So this is the way in which we solve the problem. Actually, what we have done, we have optimized the distance to be covered between cities. And how it can be optimized? When we can minimize it. And how we can minimize it? By observing that original paths have to be replaced with the new paths and having the lesser weights. Step by step, what we have seen, that we have found the graph that should be that should represent the traversing or the movement of traveling salesmen from one city to another, so that it may involve the lowest distance and hence the lowest cost. Now coming on to the graph coloring. In graph coloring, we are having two main parts. One is the vertex coloring and another is the edge coloring. What is the condition? The condition for graph coloring is that no two adjacent vertices should have same color. There should be different color, like B and G, or we can say X1 and X3, as they are adjacent. X1, X3 are adjacent, so they should have different color. Here we are having green color, or here red, because they are adjacent. So adjacent vertex should have different color. Like we are having another vertex X2. X2 is adjacent to X1, so these colors should be different. So here green, so we are having yellow and red. It's okay because X2 and X3 are again adjacent. Is it clear? Like,
Yes.
if we are having a graph like this, we are having node A and B. So how should we color it? We should color it so that one node, adjacent node, should not have the same color. Adjacent node should not have the same color. So these are adjacent node. One is blue and another is red. Is it clear?
Yes, ma'am.
So how many colors we have used? We have used two colors. So this is known as K colorable. How many colors we use for a graph? This is known as chromatic number or K colorable. For example, suppose this is a graph. Fine. And we are having three vertices. So how are we going to color it? This is A. Fine. Now B and C are adjacent to A. So B and C should have different colors. So B is having green color. Now C can't have yellow color or green color. So C can have different color. Suppose C is having red color. As the three vertices were adjacent, the three are having different colors. So this is what 3 colorable or K colorable. Fine. And this is also known as chromatic number. Chromatic number means the colors required to color the vertices of a graph. Yes. Is the screen visible to all of you? Class, is the screen visible to all of you?
Yes, ma'am.
Yes.
See,
Yes, ma'am. Yes, ma'am.
this first one. As we are having only one vertex, so one color is required. In this, we are having two vertex and they are adjacent. One is adjacent to 2. V1 is adjacent to V2. It means different color. One is having yellow and 2 is having red. See the third diagram. Vertex V1, vertex V2, vertex V3. V1 and V2 can't have same color. V2 and V3 can't have same color. So V1, V2, they were adjacent. So V1 was red. So we haven't used red color for V2. We have used yellow color. But V2 and V3 adjacent. They will have different color. But V1 and V3, they are not adjacent. They can have same color. So we have used same color for V3. Is it clear? So how many colors we required for this graph? How many colors?
At least 2.
2 colors. Fine. 2 colors. One is red and one is yellow. Coming on to last diagram. Last diagram. Here see 1. 1 is connected to 5. 1 is connected to 4. 1 is connected to 3. 1 is connected to 2. It means every node will need to have different color. Why? Because every vertex is adjacent to every other vertex. Because this is a complete graph and every node is connected to every other node. Is it clear? So how many vertex are there? 1, 2, 3, 4, 5. So we are requiring 5 colors. Is it clear?
Yes.
So chromatic number is 5. Clear, class, clear? And in this diagram, suppose here you are having a diagram, this, without coloring. And you have to find the minimum number of colors required to color this graph. Keeping in view that adjacent nodes should have different colors. Adjacent node should have different colors. Like this node is having yellow, so its adjacent node will have different colors. Suppose you have green. Is it clear? Class, is it clear?
Yes, ma'am.
Now the center one was Z, and Z is yellow color. Z is yellow color. See here. So its adjacent are y2, its adjacent is y1, adjacent is y5, its adjacent is y4, its adjacent is y3. So none of them is having yellow color. Is it clear? Is it clear? Yes, is it clear?
Yes, ma'am.
And see y2 is having purple. So adjacent to y2 we are having x1. X1 is having different color. See, x3 and x1 are having green color because they are non-adjacent. They are non-adjacent. See, green color y1, x1, y3, x3, all are non-adjacent. So they can have similar color. Is it clear? So what is the minimum number of color required to color this graph? Keeping in view that adjacent nodes should have different color. So how many colors we have used? How many colors we have used?
5.
One is green, yellow, third purple, and fourth red. So we have used 4 colors. So it is 4 colorable. Your chromatic number is 4. Is it clear? Class, is it clear?
Yes.
You have seen maps, GIS images. In those GIS images, you have seen forest, deserts, different components covered with different colors. So same type we have used here. We have used a mapping based on the colors on graphs. See here. So you can define color classes. Are you able to view this diagram?
Yes.
Yes, ma'am.
See, there are different color
Yes,
classes,
ma'am.
है ना? And different sets of vertices. For example, if you say yellow color class, so all yellow like X16, X15, this one X4, X6, X8, and X10. They X10, they are yellow color. And see, no two adjacent is having same color. Like X2 is 4, X2 is green color, X1 purple. Fine. Is it clear? So if you are given any graph, can you find the minimum number of colors required to color that graph? Suppose I have drawn a graph G. Can you find how many colors will be required to color this graph? Any one of you? Yes.
Sure, ma'am. Based on this description, we can do it, inshallah.
Yes. Suppose this is yellow color. Fine. This is yellow color. So as it is non-adjacent, it can be yellow color. Fine. Then how will you go? This is red color. So the adjacent should not be red. So
Purple.
yes.
Green. Purple.
Yes. Is it clear? Then
Yes.
in this way you can color the graph and find the minimum number of colors required to color the graph. Yes or no?
Yes.
As these are non-adjacent, so it can be blue.
Yes.
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 And it can again be red.
Right.
In this way you can color the graph. Is it clear, class?
Yes, ma'am.
Fine. So what we were doing vertex coloring. Tell me, what are two components of any graph? What are two components of any graph?
Vertex and edge.
Vertex and edge. So we have seen vertex coloring. Now we will see edge coloring. Edge coloring means we have to color the edges. See, here we are having edge coloring. Fine. Edge coloring means minimum number of colors required to color the edges of a graph. Fine. And this is known as edge chromatic number of graph. See, we have colored the edges. Fine. See, in this diagram, in the leftmost diagram, we are having three edges: 1, 2, and 3. 1, 2, and 3. All are having different color because they are adjacent. In diagram 2, how many colors are there? In diagram 2, how many colors are there? Yes. In diagram 2, how many colors are there?
I think
One
three
is red.
colors.
And in
Green.
third diagram, how many colors are there? And have you seen no two adjacent edge will have same color? Fine. Fine. So find the question is like this. Find the edge chromatic number. Can you find it? What is the edge chromatic number? Yes.
First one is
2.
first
Because
is
we are
2.
having two colors. Very good.
Second is 3.
And in second, how many colors? 3. So edge
3.
chromatic number of second graph is 3. Clear? Now coming on to planar graph. Have you heard planar graph? Have you heard planar graph, class?
No, ma'am.
No. Suppose Suppose we create a graph like this. Can you tell whether this graph is a planar graph or not?
No, it's not.
See, this graph can be represented like this. And for this edge, and for this edge, it can be shown like this. Now see, is it representing planar graph?
Yes.
Yes. So this is planar graph. Planar graph means a graph which can be represented like this, where edges are not intersecting, edges are not crossing. In this, edges were crossing. In this, edges were crossing like this. They were crossing. Here, edges are not crossing. We have removed that crossing. How? We have this edge BD from here. See, takes fine. So this is an example of planar graph. This is again the planar graph. Planar graph is means the graph that can be drawn in this manner where two edges never cross each other. Is it clear? Is it clear?
Yes.
Yes. Fine.
Yes, ma'am.
Now you know what is planar graph. See, we have different regular solids. Fine, like tetrahedron, cube, octahedron, and so on. And these can be represented as this. So all these are examples of planar graphs because they can be represented like this. Is it clear? Class, is it clear? You have represented tetrahedron like this. Yes or no?
Yes, ma'am.
So all these are representing planar graphs because they can be drawn like these. Like this 1 or 2 are same. This 3 and 4 are same. 5 and 6 are same. 7 and 8 are same. 9 and 10 are same. Only the way of representation matters. So any graph which can be represented in form where edges are not crossing each other, then we can say that graph is an example of planar graph. Is it clear, class? Now the concept is clear?
Yes.
Yes, ma'am.
Yes. So the number of region in planar graph, is equal to number of edges minus number of vertices plus 2. This is a formula to find the number of regions of a planar graph. So the number of regions of a planar graph is its number of edges minus number of vertices plus 2. Is it clear? Fine. So in this graph, find number of regions. Just find number of regions in this graph. Yes. In example 1 graph, just find number of regions. Just find how many regions are there?
It is 4, ma'am.
Yes.
4 regions. It is 4.
How did you find?
See, we have total 6 number of regions.
How many edges are there?
1, 2, 3. It is 4, 5, 6.
5 pages.
Sorry, 5.
2, 3, 4, 5, 6.
6.
6 edges. Okay. Minus number of vertex.
4.
Number of vertex 4. Okay.
4.
4 plus 2. So how many regions are there?
2.
Yes. How many regions are there?
4.
4. Fine. 4. And how can you show those figures? How many? How can you show them? How can you show them? Regions.
From
See.
B to
Yes.
C to B.
Yes.
is one region.
This is one region. This is one region.
Yes.
Fine. This is one region, outermost. This is second region, third region, fourth region. Is it clear? Is it
Yes.
clear?
Yes.
Now region is clear.
Yes.
Concept of
Yes,
planar graph is
ma'am.
clear. Fine.
Yes.
Fine. Fine. In this graph, find the number of regions. This is a planar graph, yes or no, class? This is a planar
Yes.
graph or not? Yes, it is a planar graph because there are no edges crossing each other. Fine. Now find number of regions. Let's see.
1.
Total number of edges are? Total number of
3.
edges are? 3. Number of vertices are? Number of vertices are?
4.
4. ठीक है, plus 2. What is the answer?
1.
1. 1.
1 positive.
Yes, 1. See, I'll show you. I'll show you. Complete is one reason. Complete. See, this is one reason. Yes or no? There is no boundary. There is no boundary. Complete.
Yes.
One region. Fine. Is it clear? This
Yes.
complete is one reason. There is no boundary.
Yes,
How
ma'am.
is it clear?
Yes.
Because there is no boundary separating. Na? There should be some boundary. If there should be some boundary, then we can say we are having more than one reason. But if we are having no boundary, then there is only one reason. Okay. Yes, for this one just find number of region 1. For graph number 1, find number of region. For graph number, find number of regions.
3.
What are number of edges? How many edges are there?
6.
5.
I think 5. 1 minute. 1, 2, 3, 4, 5, 6.
5.
6
Six.
edges are there. How many vertices are there?
5.
4.
4 edge. 4.
4 vertices are there. Plus 2. So it turns out to be
4 is
6 minus 4.
4
2
is
plus 2, 4. Fine. 4. So there are 4 reasons. There are 4 reasons. Can you show 4 reasons? Yes. One reason is this. Now another reason I'm highlighting with the red color. Second reason. Now coming to the third reason. This is the third reason. Is it clear, class?
Yes.
And what is the fourth reason? This entire. This is fourth reason. Is it clear now?
Yes, it's clear.
Is it number of reasons are clear? This is the fourth reason.
4. Yeah.
Everything outside this.
Okay.
Is it clear, class? Is it clear?
Yes, ma'am.
Done. So we have completed graphs. Today we have completed block of graph completely. Fine. We were having 4 booklets. Under graph, we were having 4 booklets. Fine. I'll show you. The first one was graph introduction. Second is connectedness. Third was your Eulerian and Hamiltonian graphs and traveling salesman problem. And last block of the graph, we were having graph coloring and planar graphs. Graph covering and planar graphs. Is it clear, class? So we have
Yes.
completed.
Yes.
We have completed graphs. Fine.
Yeah, it's fine.
So today, is everything clear?
Yes. Thank you, ma'am.
Yes. Now you need to practice. Fine. Now
Okay,
you need
fine.
to practice. In case you have any problem, you may ask me in further sessions. Fine.
And if you share the previous class PPT also.